Okay, so thanks so much for inviting me. This lecture is also about security, but it will explore some logic synthesis. You will also learn some of the techniques that are being used in the commercial, logic synthesis tool. But how I leverage for the security purpose, I'm going to explain today how I actually hide the hierarchy of digital IP, right? So that is the main goal here. So before moving further, this picture is, it reminds you a lot because I have displaying this one in the last two lectures. So the goal is like, I will recap a little bit. Some of the new students are there. So we have many, stages in the globalized IC supply chain and the design flow, right? So the design flow is kind of systematic, but the IC supply chain is, it involves multiple entities, right? So when the design is sent, right, we have a lot of control. But when the design is sent to foundry, we don't have any control. I cannot go to Taiwan and see what these guys are doing, right? Okay, then we have fabrication, right? After that fabrication, I cannot go to Malaysia. How they're packaging? Are they putting something in the maybe in the package or hiding something like you know? And the most complex problem is the deployment. When we have PCB, we have multiple components. It comes to my company, and I cannot see which transistor is what, which resistor. Is there have any modification or blah blah blah. So we have a lot of problems with this globalized IC supply chain. For example, on this level we can see it because the fabrication is the thing that is the main job, right? And the adversary or the foundry, right? It has huge control. And they can manipulate transistor level information, believe me, right? So they can do whatever they want. If there is some person inside the foundry, like in TSMC or Intel, he or she is wanted to do something, he or she can do, right? So that is the fact. So we can have reverse engineering. This is the major problem. Reverse engineering is like that. You get the logic, you copy the logic, and sell it in square or black market. Or the foundry can also overproduce the IC, right? I give you the order of 5,000 chips, and they fabricate 1 million. Who knows? We don't have any control, right? And the hardware Trojan, one of the biggest problem. This is the reality. No one can say that. We can escape from the hardware Trojan, right? It has been happened for military purpose. It has been happened for to destroy the business model, right? A lot. IP piracy, it is the day start problem. The day you hire a the design engineer, the IP piracy problem starts. It can happen, from third party, IPs. It can happen from here. You hire a guy and this guy just put something inside it. It can be a logic synthesis. It can be place and route. Here, no one knows. Counterfeiting, yes, this is after fabrication problem, because counterfeiting is the thing like we have, like, for example, 555 timer IC, right? It's analog IC, and it has been used for example 10 years. Now this IC is degraded. It has low reliability, right? I replaced that new component with the old one, and and then we put, we can say, new package. Inside it's old IC and it's degraded component and it's not counterfeiting. So these are problems we have. We have a global sketch now. What are the problems? So there are solutions, right? The solution is distributed manufacturing. I will explain this one, what it is actually. Then we have design control logic. Logic logging we discussed in the last lecture, right? All of these techniques, they want to what? They want to secure or hide the logic, right? But the bad news is that none of them is adopted on a commercial scale. None of them, they were used for military purpose, but no one is adopted as a standard or in the industry. Okay, What is this chiplet manufacturing, right? If you see this picture, many of you knows that we have IC layers, right? IC is not like well, some wires. They have layer by layer. When the lithography, it moves, it actually develop layer by layer. Usually we have metal stack when we do the IC fabrication. When we do the, we will get PDK. There are the, lab files, maybe you know it. They have these all information, what metal is there and where, right? And what is the mathematics, or we can say what is the metal size, what is the length, what is the weight, what are the rules and language, some of them. In that case, for example, we have upper level metals, we have lower level metals like M1, M2, M3. They are used to, uh, describe transistor. Now what we do, we actually route and place, and we actually cut the design into the backend layer and into the front end layer. Front end layer has low level information. It has transistor and very low level routing, right? For example, we have polymetals. They are in where, right, in transistor, and then we have major routing here. So we send one part to fabricate in a trusted foundry, for example, TSMC, right? And the other part, no one knows where it is gone, in which part of the world. For example, Intel, right? And when they both come and we join, and then we make a design. So in that case, one of the foundry has half design, and the other of the foundry has half of the design. All right. This is called chiplet manufacturing. We chiplet and manufacture in different places. Now what we have design camouflage. At some point, this technique was actually adopted, and it was used a lot. Okay, how does it work? If we come from the analog mental view, analog point of view, we can see that, for example, this design is XOR, right? And this design is also is AND, right? This cell, sorry, logic cell. So we try to build the cell which are functionally equivalent. Functionally different, inequivalent, but they look similar or equivalent from the visual inspection, right? When we do, for example, SEM analysis. So similar is the case for with this cell, right? So this is called design camouflage. For example, for these two cells, they are actually AND and OR, right? But they look visually kind of the same. So this requires a lot of effort on the analog side. So this was when we design some cells, and then we write our own library files and PDKs kind of thing, and then we use that to implement the design based on all logical systems. This is the logic locking. I have described this one. This is kind of thing that we insert some extra cells, or we can say gates, and then we actually embed the key cells, and we have a correct key, then we have correct functionality, and otherwise we get wrong functionality. This is reverse engineering. This is called 3D reverse engineering. Reverse engineering is not big problem right now, believe me. We can hire a company. There are, for example, in France, I don't remember the company name. You pay them, and they will give you the reverse engineering, right? Netflix easily. So the fact is that reverse engineering is like you want to get the visual inspection of all the layers. The IC from different views, and then we try to stitch, and then we try to build the logic. I explained this one in the previous lecture, but here it, and then we have also 3D view. And then we try to get all this logic back in from the IC. So all these techniques they want to do, they want to secure the ICs, but none of them is actually, what we can say, adopted and, adopted on a large scale, we can say, right? Okay, so the goal of this work that I'm going to present, very simple. The thing is that you have a lot of designs where you want to replicate the IPs, right? You want to instantiate that IP or that module, for example, sub-module in the netlist many times, right? So if what I do, if I take one module, right, for example, instance 1, 2, 3, and this is the original design, there is no obfuscation. If I try to hide one of them, because many of the instances are same, they have similar functionality. If I hide one of them, if the attacker can guess any of them, he or she will say, okay, I think the other one are also same, so okay, this one is also same, and I will put that functionality, and locking the same one, it doesn't make any sense. Okay, let's do the same thing. Now I have 50 designs which have similar functionality in the big SOC. If I lock one design with the same technique, I have to lock the other designs with the same technique, right? And if the attacker can get one of the key, he or she can unlock all of the key, right? The modules. Okay. Now I come with an idea, right? So I want to do what? I want to obfuscate all of the modules while having the similar functionality but the different hierarchy. Different hierarchy means every module has different structure. If I do the structural analysis, if I try to see the netlist and try to match both of them, I will see, oh, it will not have similar structure, but similar functionality. And if I do the different structure for every of the module that have similar functionality in the big SOC, it means I can hide the logic, right? Okay, let's try to analyze this one from the reverse engineering. If I will do the reverse engineering for all of these things, then I will see that it has different structure, right? And it is a complex process in case of repeated modules. What we did actually, what was the methodology? In the flow, we can say we have RTL, we provide timing constant, we give a standard cell library. For example, the Liberty file. Liberty file has power information, timing information for different corners, and blah blah blah. We have commercial synthesis tool. One of our best friend, right? The Genus from Cadence. And then we have different things, what we can do. We have different optimization technique, right? We can apply targeting, we can apply optimization 1 and B, we can combine different optimization technique, and then we can say don't use this technique, or don't use that technique. And then we have netlist, we have this is the important part. We do the data flow analysis. This is kind of structural analysis. I will present it. And then we do the hierarchical analysis, and we see that is it really generating the different structure or not, right? This is the report. Okay, these are the techniques that are available in the commercial synthesis tool. For this purpose, we use the GPS correlator. GPS correlator has, a lot of modules that are repeated multiple times, and it is integral part of, GPS hardware. So we have clock getting, right, to save the power. We have ungrouping. We have data path analytical. All these techniques that I'm presenting here, I suggest you, when you open Genus tool, you go to CDNS help and type all these techniques, right? And then you will see, actually, it will show all the examples. It will show you all the theory that, what actually they do. We have bubble pushing, right? We have Titan max transition. We have retiming for delay, retiming for area. Now, then we can combine all of these techniques and we can make many combinations, right? Let's try to see what happens. We have this baseline design, right? This is the minimum and maximum area, okay, right? And then We have clock getting applied. We have leakage and dynamic power also, and we try to see. So we can see here what is happening with the area. So we get area for tire, maximum area for tiring max transition. And if the similar is case for the leakage power, right? It's burning a lot of power. It might be a robust design, right? And also dynamic power. Now we actually combined, right, these two techniques, and we can see that we have kind of area close to baseline line. Okay. Now we apply different techniques and we try to see that what happens what is the increase and decrease of the area cells dynamic leakage power. So we can see that one of the technique, this is leading in everything. And then we can say the retiming for delay is burning a lot of power, right? A lot of area. And this is very useful. Now, when we get all these techniques, we combine these techniques and we run multiple experiments in, we can say, in hundreds. We got multiple, we got hundreds of the structural net lists, we can say, right? By combining all these techniques and also the individual optimization technique in the genus. And if we map them onto the probability distribution curve, and we can see where this is the baseline and where is the mean value, right? And we can see the behavior for both area cells and we can say the leakage and dynamic power. Now let's move to the interesting part of this presentation. We have used a tool. It's called DANA. It is the kind of simple, or we can say a reverse engineering tool. It actually analyzes the structure and it actually combines different flops and try to see the data path actually, right? So we use that one, and then we try to see that what happens. So this is our baseline design. We do not do any optimization tips. We have this kind of structure. We can see here this is the register size, 20 flops, right? This is the register size, we can say. Now we did a clock gated design. Can you imagine that how this structure is changed, how the connectivity, how the grouping of the flops has been changed? And similar is the case for retiming delay, and then we combine that one of the technique, and what happens with this one, we get a very different type of structure. So we can see that when we use these optimizing techniques, we can actually interact with the structure, and we can try to see if we can get different structure, right? So overall, these the repeated modules that are in the big design, right? They are actually we can say part of every design. Literally, in many of the design, you have to repeat the design, especially in the cryptographic design. Some of the structural part, we have different rounds that we repeat many times. And this means the structure is repeated many times. So it can help to prevent that type of things even for the cryptographic course. So what we did today, we can see that the design with repeated modules, repeated logic, repeated functionality, we can say, or we should not say repeated functionality actually. Repeated structure, it is really highly vulnerable to reverse engineering, simple reverse engineering. We don't have to do the rocket science, right? We leverage very, very basic logic synthesis and optimization to hide their structure. And we have very fully automated tool, kind of, right here I just presented, right? And then these optimization techniques, mix of the optimization techniques, these hybrid optimization techniques from the genus, they can really infer the structural part of the design, right? And this is what we call obfuscation. This is kind of natural obfuscation that is happening. So that is the we can say that motivation that I would like to put here. I'm happy to take your questions.